Okay, so I've got the chat open. So as I'm going along, I'll be going over quite a lot of examples as well. So if you've got any questions as I'm going along, just drop them in the chat. I'll start off with year 12 differentiation first, and it'll move on to year 13 differentiation. So it's everything you need to know for differentiation. So the start of calculus. So there probably will be quite a bit that you've not seen before, but it's quite good to see anyway. So we'll just jump straight into it because we've only got 1.5 hours and we're covering 2 years worth of content of it. So what is differentiation? What's the purpose of it? So when you're back in GCSEs, when you were finding the gradients of graphs, most likely you were finding out of a straight line graph. So essentially on this straight line, no matter where you find the gradient will be the same across that whole line. But if you've got a curve, so let's draw a cubic graph like so, you can see it starts off with a positive gradient. So this part's positive. It then goes to no gradient, and then a negative gradient, and then no gradient again, and then another gradient. So the gradient's different everywhere. So what you do is you would differentiate this curve to find out the gradient function. So you can find out the gradient at any point on that curve. So that's the main gist of differentiation. It's figuring out the gradient of a curve and finding out certain points like the maximum, the minimum, and so on. So that's the whole purpose of it. And depending on what the function is, depends on how complicated it gets with it. So it can quite quickly get complicated. So I'll just write a definition here. So dy over dx is when you're differentiating function y. So that's the function you're differentiating with respect to x. So that is what the function is in terms of that you're differentiating with respect to. So for example, y equals x squared plus 2x plus 3. You're differentiating y with respect to x because it's a function y that's in terms of x. So just be aware of that. And how do we actually differentiate? So the rule is, so to differentiate, we'll say x to the power of n. What you do is you decrease the power by 1, but you make sure before you do that, you times the front by that. So the rule is you times the front by n, so the power that it is, and then you decrease it by 1, so n minus 1. So I wouldn't recommend learning it like this. It's better to just understand how you actually do it rather than memorizing the rule. So let's take this top one as an example. How do I differentiate this? So I'm finding dy over dx. So remember the gradient function is what it is. So times the front by 2. And then I'm decreasing the power by 1. So 2 minus 1 is just 1. I'm not going to write x to the power of 1. I just leave it as is. Over here, we've got 2 times x. There's a 1 here. So 2 times 1 is just 2. And then x, 1 minus 1 is 0. And x to the power of 0 is just 1. So we do not write that down. And then differentiating 3, if you differentiate any number, it just becomes 0. But there's no point writing 0. So you can just leave it just like that. Okay, one other thing you also need to remember as well. So the notation for differentiation, most of the time you will see it as dy over dx because you'll be given a function in terms of y. But sometimes they might say f of x equals x squared plus 2x plus 3. This time you wouldn't write dy over dx, you would say f prime x. So this is also notation for differentiation as well. And it's exactly the same function as before, so the answer would just be 2x plus 2. So just be familiar with both these notations for differentiation. Okay, so that's how you differentiate. Let's do a few different examples. Okay. Let's try a different one where it's a fraction. So we'll say let's let y equal 1 over x squared. So how do we differentiate this? Well, we can't differentiate in its current state. This is where your indices rules are quite important. So you have to rewrite this, and we're bringing the x to the top. And to bring the x to the top, the power changes to minus 2. So now we can differentiate this after rewriting it. So times the front by minus 2, and then decrease the power by 1. So minus 2 minus 1 is minus 3. I wouldn't recommend leaving your answer like that. So you'd put the x back underneath just to get rid of that negative power. So minus 2 over the x to the power of minus 3 goes underneath and it becomes x cubed. And that's your answer. Okay, let's do a different one. So let's this time let f of x, just so we can get used to the notation, equal the square root of x. And you're told to differentiate this. Again, using the indices rules, I'm going to rewrite this, and I'm going to rewrite it to x to the power of a half, which is what square root is. And now applying our differentiation rules, I'm going to times the front by a half, and I'm going to decrease the power by 1. So a half minus 1 is minus a half. Let's rewrite that. So I've got a half. I'll leave that for now. Let's deal with this. We've got x to the power of minus half, which is 1 over x to the power of a half. This x to the power of a half is the square root of x. So I could just say 1 over 2 root x. And this is why in year 12, so any of you, for your year 12 students, this is why they emphasize so much on indices rules, because it starts appearing all over with the more complicated stuff. Okay, we'll do one more example, and then we'll move on to the next thing. So let's so this is question 3. I'll also send all these out as well to your email after as well, so you've got all the notes, and there'll also be a video on it as well. So let's let y equals 6x squared plus 4 over the cube root of x minus 2 over x squared plus 1. So let's differentiate this. So first things first, before differentiating, we need to rewrite this all in terms of indices. So y equals 6x squared is fine. 4 over root x, cube root x. So cube root of x is written as x to the power of a third. Now, because it's on the bottom and we're bringing it to the top, it's x to the power of minus a third. So it becomes 4 x to the power of minus third. Then we've got minus 2 over x squared. To bring the x squared to the top, it's going to be to the negative power. So it's 2 to the x to the power of minus 2, and then the 1 is completely fine. So we've rewrote that. Now let's actually differentiate. dy over dx equals 6 times 2, which is 12, and then decrease the power by 1, so just x, plus, well, not plus, 4 times minus a third is minus 4 over 3, x to the power of minus third minus 1, so 1 is 3 over 3, so minus 1/3 minus 3 over 3 is minus 4/3. If you're not too confident doing that in your head, use your calculator. You don't want to make a mistake there. It's not worth it. Okay, and then minus 2 times minus 2, which is plus 4. Be careful of your negative signs. X to the power of minus 2 minus 1 is minus 3. And then the differential of 1 is just 0. So that's nothing. Okay, I'm just going to rewrite this here rather than starting a new one. So I can leave 12x as is. Plus 4 over 3. I'll just leave this here for now. We can simplify it. X to the power of minus 4 over 3 is 1 over x to the power of 4 over 3 plus 4 over x cubed, because it's x to the power of minus 3. Okay, just simplifying that, I get 12x plus 4 over 3x to the power of 4 over 3 plus 4 over x cubed. Most of the time they will, actually there's one mistake I've just made here. There should be a minus here. So do you see how there's a minus there? That should have been a minus there. Okay, there you go. Can you not just leave it in the form when you differentiate it like originally? This here, I would not recommend leaving it like that in the exam. The examiner would expect you to not leave things in the form of a minus power. And in the question as well, it will prompt you as well to give it in this certain form. So they'll kind of lean you that way. But even if they don't, you should not write it with negative powers. Okay, so that's that one. Let's move over to the next thing. So we spoke about the fact that differentiating the curve gives you the gradient function. So you can use that to find tangents and normals. So let's do an example question. Okay, so just before doing that, I just want to explain the difference between a tangent and a normal. So let's say I had a curve like so. And I was told to find the tangent of this curve at this point here. Now the tangent to that curve is just a straight line that's drawn like so. So that is the tangent to the curve at that point. So that is a tangent. The normal meets the tangent at 90 degrees, so it's perpendicular. So the normal of that would be, I'll do it in a different color so you can see it better. The normal to this tangent would be at 90 degrees. So remember, with the gradient, it would become the negative reciprocal. So that's the normal, so that's in red. So it's quite common for them to ask these kind of questions. So let's do an example question. So the question says, find the, I'm not going to write the full question, but find the tangent of the curve y equals 4 minus x times x plus 2 at the point 2, 8. Okay, so find the tangent of this curve at the point 2, 8. For 2 seconds so I can draw the graph, just the normal line. Yeah, that's fine. I'm going to send all these notes out after anyway, just in case I'm going quite fast. Okay, so this question, finding the tangent to this curve at this point. Now, first things first, you need to realize a tangent's a straight line. And in GCSEs, you use y equals mx plus c. But for A levels, it's better to use y minus y1 equals m times x minus x1. So that's the equation of the line. Okay, so this is what we need to find. So we already know our y1 and x1. That's just this point here, since that point lies on the tangent. So we just need to find m. Now remember, m is your gradient. So we need to find the gradient of this line at this point here. So to find the gradient, we're going to differentiate this curve. So before doing that, we need to rewrite this. So we're going to say y equals, let's expand this, 4 times x is 4x. 4 times 2 is 8. Minus x times x is minus x squared, and then minus x times 2 is minus 2x. Simplifying that, y equals, I'm just going to put it in term order. Is that the equation? Because if it is, where would the y-intercept be? Because there's no c in that equation. This is basically an equation where you don't need to find c. That's the reason why it's more simple, Alex. So y equals mx plus c. The GCSE version, you have to find c, so where it crosses the y-axis, so when x equals 0, and the gradient. However, in this version here, we don't need to find c. We just need to substitute a point that's on the line. In this case, it's going to be 2, 8. So I would highly recommend for A level practicing this version here, not y equals mx plus c. But they are the exact same thing. If you do want to use y equals mx plus c, you're making it harder for yourself because you've got two things to find. You've got the c as well as the m. Okay, so simplifying this, minus x squared, 4x minus 2x is 2x. And then we've got plus 8. Okay, so we've got the equation. Now we just need to differentiate this. Dy over dx. Remember, we're differentiating because we're finding the gradient, which is m. Minus 1 times 2 is minus 2. X to the power of 2 minus 1, which is 1, so that stays as is. Plus the differential of 2x is just 2, and the differential of 8 is 0. So the new one only involves the gradient, and you don't need to worry about the intercept. I've understood that right? Yeah, that's perfect. That's exactly why we do it. We're just focusing on the gradient because they've given us a coordinate. To be fair, I don't know why they don't teach this version in GCSE, because it would work better, if anything, because you're only finding the gradient. Okay, so we've got dy over dx, but we've not got our gradient. So what we need to do is, because we're finding the gradient at this point, we need to substitute that into dy over dx. So dy over dx, so I'll say at 2, 8, dy over dx is, we're substituting x in because x is 2, minus 2 times 2, which is minus 4, plus 2, which just gives us minus 2. So we've got our gradient. The gradient is minus 2. So we can substitute this into the equation now. This equation here to find the equation of the tangent. So y minus y1, which is 8, equals m, the gradient which we've just found is minus 2, times x minus x1, which is 2. Expanding this, y minus 8 equals minus 2x plus 4. And I'm going to bring the, so dy over dx is basically the gradient formula. Yeah, that's exactly what it is. That's the purpose of dy over dx. So y equals, I'm going to plus 8 to the other side, minus 2x plus 12. And that's the equation of the tangent. So let's do an example where we've got the normal now. And I'll use a bit more harder of an example for, well, actually, just to save time, because there's quite a lot of things we need to go through, I'm going to find the normal to this equation here. So I'll do part 2. And let's say for part 2, instead of finding the tangent, we're finding the normal this time. Okay, so find the normal to the same curve at the same point. Now, the normal, just looking above, the normal is also a straight line as well. So again, the equation is going to be y minus y1 equals mx minus x1. It's exactly like in GCSEs when you know there's a straight line that you're finding, you were quickly writing y equals mx plus c, but this time you're writing this equation. Yep, it's a negative reciprocal. So we've already got our x1, y1, which is this here. So 2, 8. And we just need to find the gradient at that point. Now, because we've already found dy over dx of the tangent, all we need to do is the negative reciprocal. So the negative reciprocal, so I'll just say m equals, remember minus 2 is minus 2 over 1. So flipping that over, we get a half and changing the sign from a negative to a positive. So our gradient is a half. So our equation is y minus y1, which is 8, equals m, which is a half, times x minus 2. Let's expand that. Y, actually, I'm going to times this 2 up over here. The 2y minus 16 equals x minus 2, just to make it easier to simplify. Plus 16 to the other side. 2y equals x minus 2. Add 16 is 14. So I'll just leave it like that. But to be fair, if they said we put it in the form y equals, just divide the whole thing by 2. So it's a half x plus 7. But they'll always tell you what form in the exam questions that they give. Okay, let's move on. So that's tangents and normals, which are the straight lines. Now, what I'm going to cover next is stationary points. Now, what a stationary point is when the gradient is 0. Stationary points happen when the gradient equals 0. So think back to GCSEs. It's like when you've got a graph that's a straight line, like horizontally or vertically. Think of that on the graph as well. So let's look back at this cubic graph. We can see there's 2 stationary points here, or in this color. That's a stationary point there, and that's also a stationary point because that's where the gradient equals 0. And we've just been saying that the gradient is dy over dx. So therefore, to find the stationary point, we just need to make our gradient function dy over dx equal to 0 to find out when them stationary points are. Okay. So that's what a stationary point is. Let's do an example. The best thing with A-level maths to practice is just go over as many examples as possible and a lot of worst case scenarios. So the question says, find the coordinates of the stationary points. So as soon as you see stationary points in an exam question, straight away you should be thinking dy over dx equals 0. So find the coordinates of the stationary points of the curve y equals 2x cubed minus 3x squared minus 12x plus 5. Okay, so stationary points dy over dx equals 0 is what we need to solve. But first we need to find dy over dx. So the differential is 3 times 2, which is 6, decreased power by 1, minus 6x minus 12. Okay, that's our differential. Now we need to make this equal to 0 and solve it. 6x squared minus 6x minus 12 equals 0. And that's what we're solving. I can divide the whole equation by 6. So x squared minus x minus 2 equals 0. We've got a quadratic. We're going to get 2 answers. 2 numbers at times to give you minus 2 and add to give you minus 1. X minus 2, x plus 1. So therefore, our stationary point So it says coordinate of the stationary points. Remember that. So we found just the x part. So x equals 2 or x equals -1. But that's not our final answer because we've not found the coordinates. We've just found the x values. So to find the coordinates, so the y part, we need to substitute these two separately, obviously, back into the original equation to find out what's the corresponding y value. I'll just do it in red over here. So when x equals 2, I'm going to just substitute in here, but I'm not going to do it just because of the sake of time, but you'd substitute 2 in. So 2 cubed is 8 times 2, which is 16 minus so on. So when you substitute that in, you get y equals 12. And when x equals -1, again, substitute that into the equation to find y. So -1 cubed minus 1 times 2, which is -2, and so on. Keep substituting it in. You end up getting y equals -15. So have a try at that yourself in your own time. So our two coordinates of where the stationary points are is 2, 12 and -1, -15, which makes sense for there to be two stationary points on a cubic graph because a cubic graph looks like this, where we've got two stationary points. So that's what that means. Okay, so that's what stationary points is. Now, what you should have noticed as well is, with these stationary points, one is like, how did you substitute so quick to get the answer? I've got the answers here, Alex, just to save time so we can go over more topics because we've only got an hour ahead. But yeah, just substitute that in your own time as well and see if you get the same answer as well. Okay, so as I was saying, we found out stationary points are when the gradient equals 0. Now, 1 is a maximum because it's like the top hump of the curve, and 1 is the minimum. So we can also figure that out as well from the differential equation, and that's where the second differential comes in. So when you differentiate again, you can figure out whether that stationary point is a maximum point or if it's a minimum point. Okay, so let's do an example of that. Well, before jumping onto an example, there's a fact that you need to know as well. So we find the second differential, and the notation for the second differential is d2y over dx squared. Or if we're using the f prime example, so just looking above, remember we said you can use this notation as well. F prime of x, if you put two primes, the f prime prime x, that's the second differential. So that's the same as d2y over dx2. Yeah, so what does finding the second differential get? So this is the second differential is going to tell us whether these 2 points are maximum or minimums. Because we can't always draw the graph, sometimes we just want to find it out from differentiating. Okay, so that's what it's telling us, whether it's a maximum or a minimum. I'll just write max or minimum. Okay, so the rule is, so that's the whole point of the second differential. If the second differential is less than 0, so when you plug it in and you get less than 0, that means it's a maximum point. If your second differential, when you plug in your x value of the stationary point, is more than 0, then that means it's a minimum point. So we'll do an example. We'll continue the last example actually, because they'll follow on quite nicely. So I'm just going to copy this down at the bottom. So these two stationary points I found, I just want to figure out, are they maximum or are they minimum points? So I'll just paste it over here. So I'll just say continuing above question. Okay, let's differentiate this again. So we're finding d2y over dx2. 6 times 2 is 12, decrease the power by 1, which is x. Is it not obvious though? One is negative on the x-axis and one is positive, but you don't know which one it is. Your curve could look like the one I've drawn above, like that, but what if it was the other way around instead? What if it's like that? What if this one's the minimum and that's the maximum? So it's not, it can be obvious with cubic graphs, but you'll soon come to realize when you start doing exponential graphs, logarithmic graphs, then it's not that obvious. This is just an easy example I'm using, which is why it's obvious. Wouldn't the cube be negative then? Yeah, it would be, but I'm just giving an example. This is an easy example, so it is obvious, but it's just to show you the idea, so you can relate it to a real life example. But when you start doing stuff like parametric equations, and like Cartesian equations and such, it gets more complicated. So just keep that in mind. So differentiating this again, we get 12x minus 6. Okay, so we've got 2 points where there's a stationary point, this one here and this one here. So we need to substitute each of the x values and see what happens at d2y over dx2. So I'll just do it in red. I'll say at x equals, we'll do the first point, 2, which is, we know it's a stationary point because that's what we found. So at x equals 2, d2y over dx2 is 2 times 12, 24, 24 minus 6, which is 18. Now 18 is more than 0, so that means at x equals 2, this is a minimum point. Okay, now let's do the next point. At x equals, what have we got next? X equals minus 1. Let's plug that in. d2y over dx2 is minus 1 times 12, which is minus 12. Minus 12 minus 6 is minus 18, which is less than 0. So therefore, that's a maximum point. So it might be obvious because you know what the graph looks like, but again, it's for the sake of knowing for curves that are not so obvious. Okay, that's maximum and minimum points. Okay, now I'm going to introduce another concept, and this is whether a function, do it in purple. So a function is increasing or decreasing. Now I'll just explain what I mean by this. So if a function is increasing, the graph would look like this. Let's draw this. Okay, so if a function was increasing, the graph would look like this. So as x is increasing, y is increasing. So that's an increasing function. However, if the function was decreasing, as x is increasing, then y is decreasing. So it would look like this. So that's what I mean by increasing and decreasing functions. So as you can see here, if a function is increasing, the gradient is positive because it's going upwards. Yeah, positive versus negative gradient. That's exactly what it means. So a positive gradient. And if a function is decreasing, it's a negative gradient. So it's a really common exam question that they say, like, is the function increasing or decreasing? You would find the gradient and you would see, is it a positive gradient or is it a negative gradient at that point? Okay, so I'm going to do an example question. This is a past exam question. Out of curiosity, what exam boards are you all doing for A-level maths? The differentiation topic doesn't really differ much from AQA, Edexcel, and OCR, but what exam boards are you all doing? Edexcel is the most popular one, I think. Okay, yeah, it looks like Edexcel is a popular one then in that case. But this is taken from an Edexcel past paper. So the question says, find the range of values. So range means like a multiple set of values. So you're going to get an inequality. So find the range of values for which the graph of f of x equals 4 plus 3x minus 2x squared is increasing. So how would you find if a function is increasing or decreasing for a positive quadratic, since both doesn't? How would you find a function is increasing or decreasing for a positive quadratic, which basically looks like this? Since that does both. Yeah, but they will say which range of values. So can you see in this question that I've just done, the range of values for which f of x, so this here, which is a negative quadratic, so it's an n-shaped graph, for which is increasing. So I'm just finding just this part. I'm trying to find the range of values, just that part there. So yeah, a graph can do both, you're right, but we're just finding the range. Okay, so for this question, the range of values is increasing. So because it's increasing, I'm finding out when the differential is more than 0. So I'm finding the positive gradient. So that's what I'm finding when f prime of x, the differential, because we've got f of x, is more than 0. So that's what we're figuring out. Let's find the differential. That's the differential of 4 is 0. Differential of 3x is 3. minus 2 times 2, which is 4x, because decreased by 1. Okay, so that's our function, our differential, sorry. And we need to find when this is more than 0. So I'm going to write that and just write more than 0. And I'm just solving this for x. So it's just an inequality. I want to make this minus 4x positive. So I'm going to bring it over to the other side. 3 is more than 4x. When you get x by itself, I'm going to make x first. So this is saying 4x is less than 3 because that's where the pointy side is. I'll write that like this. I need to get x by itself, so I need to get rid of that 4. So x is less than 3/4, and that's our answer. So the range of values for which this function is increasing is when x is less than 3/4. Okay, let's move on. So the next thing I want to cover is convex and concave curves. So I'll just define this first. So what is a convex and concave curve? Has anyone heard of convex and concave curves, or have you not really done this before? So convex, concave. Physics, you've heard of them. Okay. So again, it's just some rules that you need to know. So convex and concave, obviously it's a bit obvious for the increasing and decreasing graphs that we've done, but with this, all I would say is just memorize it. Now, a convex curve, again, this is to do with the second differential again. So a convex curve happens when the second differential is more than 0. And when it's a concave graph, it's when the second differential is less than 0. Okay, so just to show you what the graphs look like, I wouldn't go too deep into these because you can go quite deep and then you can get really confused. I would just say memorize the rules and the graphs of what they look like. So a convex graph basically happens when you've got a graph that looks like so. So essentially, your gradient is increasing. So it's like an increasing graph. So that's a convex curve. Whereas your concave graph looks a bit like the decreasing one. So it's concave and it comes like that. So you'd say x values are like below the curve. So that's your convex and concave. So I want to show you a past exam question that does test you on this. So got a past exam question here. So this is saying, okay, so we've got f of x is this. This is taken from a paper 1, or is it paper 2? I'm not too sure. But part A says find the second differential because it's got 2 primes. So let's find the first differential. 3x squared, so 3 in front, decreased power, plus 2 times 2, which is 4, decreased power by 1, minus 8. So we found the first differential. Let's find the second differential. 3 times 2 is 6, decreased power, and then the differential of 4x is just 4, and then minus 8 is just 0. Okay, so that's how you find the second differential. BI says, hence solve the second differential equaling to 0. So to compare with the concave, depends on which way they face, because I'm assuming positive quadratic is concave and negative is convex. Yes, I would say look at the way the graph is, but the thing is they don't always give you the graph. You might get a function that you've not recognized before, so I wouldn't think too deeply about what the graph looks like so much. I would focus more so on the second differential being less than 0 or more than 0 and which one it is. Okay, so solving this here, I'm going to make this equal to 0. So 6x plus 4 equals 0. 6x equals minus 4. So x equals, divide by 6, minus 4 over 6, which is just minus 2/3. Okay. Part BII says, hence find the range of values. So again, it's a bit similar to the increasing and decreasing functions question. It's exactly the same, more or less, but it's just using different words, concave and convex. So hence find the range of values of x for which f of x is concave. Now going back to our notes, we said concave is, that's concave. Okay, we said concave is when it's less than 0. So all we're doing is making the second differential less than 0. So well, in this case f prime prime of x, we're finding it when it's less than 0. So f prime of double prime of x is 6x plus 4. That's less than 0. So this is just what we're solving, which we've kind of solved up here when it's in terms of equal to 0, but I'll do it again anyway. So 6x is less than minus 4. So x is less than minus 4 over 3, which is just minus 2 over 3. And there you go. That's your answer. So I wouldn't say overcomplicate it too much. I've seen like students overcomplicate like concave and convex and try to figure out what the curve looks like. Just remember your second differential rules and you'll be fine from there. Okay, let's go back to the next topic. Okay, so that's convex and concave curves. Let's move on. Okay, so the next thing we're going to cover is a chain rule. This is a year 13. Is it year 13 topic? Or they've done it in year 12. Have any of you heard of the chain rule before? Okay, so the whole purpose of the chain rule is if you're differentiating functions inside a function, so there's double functions basically. Now, the basic rule is if you're finding dy over dx and you get a function, so let's say I've got y, which is a function of x. But that function of x, it's too complicated to just differentiate alone. So what I can do is that function of x, I can write in terms of a new function of t. So this will make more sense in an example. Some people use u, some people use t. It doesn't really matter. You just introduce a brand new variable. You can then differentiate this. So you can then differentiate your function that you've just figured out and plug it into the original to cancel out. So I'll put it in an example so it makes more sense. But the basic rule is dy over dx equals dy over dt times dt over dx. So what that basically means is using your normal fraction rules, you can see why this works. You can see that these dt's here, they cancel out with each other. So you're left with just dy over dx anyway. So that's why you can find dy over dx by finding dy over dt and then timesing that by dt over dx because they cancel out. Okay, so let's do an example so you can see it in action. So let's find dy over dx when x equals 1 of y equals 1 over the square root of x squared plus 4x. Now here, I can't just differentiate this normally, so I'll show you why. The first step is I want to bring whatever's underneath the denominator to the top. So the square root changes it to, on the bottom anyway, x squared plus 4x to the power of a half, and bringing that to the top, that becomes minus half. So y equals x squared plus 4x to the power of a half. Now we can't differentiate that as is because it's a function inside another function, so we can't just differentiate it. We have to use a chain rule. So we need to define a new equation, and this new equation I'm going to call t. So I'm going to say let t equal this thing here. So x squared plus 4x. So I've just defined a new function t in terms of x. So now, because I've introduced this, I can rewrite this equation and I can say y equals t, because I've just said that's t, to the power of a half. So I've just introduced two new equations, which I'm going to find these of to find dy over dx, basically. Some people use u, but because u comes up like in the product rule and other rules that you're going to come up to, I like using t for the chain rule. So let's differentiate both of these. Now here I'm differentiating t with respect to x. So depending on what your equation starts with and what it contains depends on what you're differentiating. So always check that out. So we're doing dt over dx here. So differentiating that, we get 2x plus 4. Okay, the bottom one, we're differentiating y with respect to t. So it's dy over dt. Bring the half to the front. T, and then a half minus 1 is just minus a half. Okay, so we've differentiated both of them. Now we just need to substitute into here, but before doing that, we need to get rid of anywhere where there's t inside these new differential equations, and it's right here. I don't want that t there because my original is going to be just in terms of x because it's dy over dx. So all I need to do is just change that substitution. It is a half, well, I can rewrite that first. I can say a half times 1 over t to the power of a half, which is just square root t. So that just becomes 1 over 2 root t. So therefore, substituting t into here, what have we said t is? T is 2x plus 4. So I can just say that's 1 over 2 square root of 2x plus 4. So that's where that comes from. So now to find dy over dx, all I need to do is just plug these into the chain rule formula right here. Bring this a bit down. Okay, so dy over dx equals dy over dt, which we've just found here, which is 1 over 2 times 2x plus 4. And we're timesing that by dt over dx, which is 2x plus 4. So we're just timesing these two with each other. T is x squared plus 4x. Good spot. I did not spot that. Okay, good spot. So this t here is x squared plus 4x. Okay, yeah, that's perfect. So let's put that now into dy over dx. Is dy over dt, which is 1 over 2 times x squared plus 4x. We're timesing that by dt over dx, which is 2x plus 4. That just gives us 2x plus 4 over 2 times x squared plus 4x. Okay, I'm just checking all that is right. Okay, and then all we're doing is we're just plugging in x equals 1 to here just to find out what is dy over dx when x equals 1. So 1 times 2 is just 2, 2 add 4 is 6 over 1 squared, which is 1, add 4 times 1, which is 4, 1 add 4, so 2 root 5. So the question might say give it to a certain amount of decimal places or so on. So we'll just leave it to that really. Doesn't really matter for that one. Okay, let's do another example. Okay, this is a tricky example. So let's say x equals, so this time it's not y equals, x equals y cubed plus 2y minus 7. And the question says find dy over dx at minus 4, 1. Now, what you need to notice here, we can't find dy over dx because we've got x in terms of y. So to find dy over dx, we are going to do, well, first of all, with this equation to differentiate it, we can only find dx over dy because it's an equation of x in terms of y. So differentiating with respect to y, 3y squared plus 2. But we want dy over dx, so how can I get dx over dy to look like dy over dx? Well, I can just say dy over dx equals 1 divided by dx over dy. So just to prove that works, your keep change flip rule, that's 1 times You keep the first, change that to a times, and flip the second. dy over dx. So 1 times dy over dx is dy over dx. So to find dy over dx, I need to do 1 divided by what I've just found here. So it's 1 over 3y squared plus 2. I want to find it at this point here. So I'm just substituting the coordinates minus 4, 1 into here. So dy over dx equals, so I'll just say at minus 4, 1 over 3 times y squared, so 3 times y, so we're not plugging in x this time, it's y, which is 1 squared, which is 1, plus 2, so we get 1 over 3 times 1 is 3, 3 add 2, which is 5. So our answer is just 1 over 5. So that's chain rule, but in terms of like inverse, so like 1 over. So that's another result that you need to remember as well for chain rule. Okay, now let's differentiate the exponential logs and exponential functions. So these are the rules that you need to remember for this one. So if you have a function, so this is the first one. So if you've got y equals exponential of x, okay, here that's fine. Just give you a second for that. Okay, so if I am differentiating the exponential function, so remember the exponential function looks somewhat like that. So if I'm differentiating that, all I get is the same thing. So the differential of e to the power of x is just e to the power of x. That's your first rule. Oops, 2 seconds. Okay, your next rule. If I am differentiating, so y equals exponential of k to the x, where k is just a number, then dy over dx equals, that number comes in front, and then e to the kx, so that just remains. So just as an example, I'll do an example over here of this. If I was to differentiate y equals e to the x plus e to the 2x, the differential of this would just be e to the x, because the differential of e to the x is just e to the x. And then e to the 2x, the 2 comes in front, and then times e to the 2x again. So that just remains. Okay, and finally, the rule for logs. So if you've got y equals the natural log of x, then the differential is just 1 over x. That's another rule that you need to remember. So let's do an example in terms of that. Just do it down here. So just to show you this. Question 1. So if y equals log x squared plus 3, and I'm finding the differential of this, well, we're using the chain rule because we've got a function here. So just like last time, I'm going to let t equal x squared plus 3, which is this in here. Therefore, y equals ln t. So differentiating each of these, dt over dx is just 2x, and dy over dt is just 1 over t. So this rule that we just used up here. Okay, so now using the chain rule, remember the chain rule says dy over dx equals dy over dt times dt over dx. Therefore, dy over dx equals dy over dt, which is 1 over t, but I'm not going to write t, I'm going to put t in, which is x squared plus 3, times dt over dx, which is 2x. So I just get 2x over x cubed plus 3. So that's my answer. So that's a good example of both the chain rule and differentiating a log equation as well. Okay, and there's one other rule that you need to know about as well. I'll just write it up here, and I'll just box them as well. You've got a rule, and then there's this one as well. So if you have y equals a to the power of x, where a is just some number, then dy over dx equals a to the power of x log a. So you can show that this rule does work, but just in essence of time, you want to remember this result for the exam as well. So let's do an example of that one, and I'll just do it on a new page. And I'll bring this result down so you can see it. Okay, so the example says, find the equation of the tangent to the curve. So tangent to the curve. So remember tangent, y minus y1 equals mx minus x1. So tangent to the curve, y equals 3 to the power of minus 2x at the point a half third. Okay, so this is testing our knowledge from before as well. So find the equation tangent of the curve. So remember tangent is going to be y minus y1 equals mx minus x1, where we need to find the gradient because we've already got our coordinates. And we need to differentiate this curve to find that tangent. Okay, so how can we find dy over dx of that? Well, using our rule above, we've got y equals a to the x, but we've got a chain rule there as well. So, because we've got a function inside. So, dy over dx, I'll just do it over here, the chain rule. I'm going to let t equal minus 2x, so the function that's in the power. So therefore, y equals 3 to the power of t. Differentiating each of these, dt over dx is minus 2, and dy over dt just equals, well, 3 to the power of t would become 3 to the power of t times ln a, which in this case is 3. So I've just used the result above. Now, plug in t back into here, I get 3 to the power of t. T we've said is minus 2x. ln 3. Okay, remember the chain rule says dy over dx equals dy over dt times dt over dx. Plugging everything in. Dy over dt, which we've just found, this should have said dt over here, is 3 to the power minus 2 x ln 3 times dt over dx, which is 2. So we just get, sorry, minus 2. That's over here. So we just get, we can just leave the minus 2 to be fair. It doesn't really matter simplifying that. We're just using it to find the gradient. I'll just say minus 2 times 3 minus 2x ln 3. So we need to find the gradient at this point here. So we need to say at a half third dy over dx equals, we're just substituting a half in for x here. So we get minus 2 times 3 to the power of minus 2 times a half is just minus 1. So really 3 to the power of minus 1 is just 1/3. So I'll change that to 1/3. ln 3. So not sure how familiar you are with log rules yet. What exactly is ln? I'm a bit confused. I'm not sure. Have you covered log rules yet, and exponential rules, and well, the natural log? So ln. Have you not covered that yet? Maybe that's why you're a bit confused. ln is just a function. It's the inverse function of the exponential. So it looks somewhat. So you know how the exponential looks like this. ln x is the inverse of that. Yeah, it's just a function. Just think of it as a curve. That's all you need to think of it as. Okay, so for this, we would get minus 2 over 3 ln 3. So we found our gradient, and ln is just a number. So on your calculator, there is an ln button. So it's just, you'll get a number out of it. So that's, we found the number, we found the gradient, and we just leave it like that because it's accurate. So therefore, the equation of the tangent is y minus y1, which is a third from the original coordinate, equals m, which we've just found, minus 2 over 3 ln 3 times x minus x1, which is just a half. And simplifying that, we're going to start using our probably log rules here, I'm guessing. So y minus a third equals minus 2 over 3 ln 3x, and then minus 2/3 times minus half, minus 2 times minus 1, so plus 2 over 6 ln 3. Just double check that. And then we get y minus a third equals minus 2/3 ln 3x plus, that simplifies to a third ln 3. I've just simplified that fraction. Okay, so I'll probably get rid of the thirds, to be fair, but in the exam, again, they'll tell you what form they want it in, but I'm just going to get rid of the 3 that's on the bottom. So I'm going to times the whole equation by 3. We'll get 3y minus 1 equals minus 2 ln 3x plus 1 ln 3, which is just ln 3. So just times the whole equation by 3 just to get rid of the fractions. But again, a lot of kids get confused. How do I know which form to give it in? They will prompt you in the exam question to give it in a certain form, so don't be too worried about that. Okay, next thing is differentiating the trig functions. So there's some rules you need to remember. So differentiating the trig functions. So just to give you the rules first, if I've got y equals sine x, the differential of sine is just cos. If I have cos x, the differential of cos is minus sine. Remember, these are all results that you need to remember. And if I had tan, the differential of tan, I'm not sure if you've come across this yet, but it's sec squared x. So I'm not too sure if you've done sec, cosec, cotan. It's just one of those functions. But yeah, just if you've not done them, all they are is a different trig function. And they are essentially inverse functions of sine, cos, and tan. But you don't need to know too much about that. Just know it's another trig function. And we can prove this using a different rule, which I'll come along after, so the quotient rule, which you'll come to see as well. But for now, these are the results that you need to remember for differentiating trig functions. So let's see examples again. Okay, one thing to note as well is if I've got a number in front, so just to give an example, if I had y equals, I don't know, sine 2x, that's technically a function in a function, so really you should use chain rule, but just to save time, the generic rule is that you differentiate this, so the differential of 2x is just 2. You put that on the outside, and then the differential of sine 2x is just, well, the differential of sine is cos, so it just becomes cos 2x. So just remember that number you differentiate on the inside, you bring it on the outside. Okay, so let's do an example. Roll a tiny bit up. Okay, let's do an example. So let's differentiate y equals cos 2x plus sine of x plus 1. Okay, so for this first one, let me differentiate this part first. So just like I said before, the differential of cos is minus sine, but we've got that 2x there. The differential of, so bring the 2 out. because the differential of 2x is just 2. So it's 2. Differential of cos 2x is minus sine 2x. So that's where that comes from. Now differentiating this, I've got a function inside a function, so I have to use a chain rule. So for this one, I want to let t equal x plus 1, which is that inside thing there. So therefore, y equals, just for this part, remember, so y equals sine t. Differentiating each of these, dt over dx equals just 1, and dy over dt equals, the differential of sine t is just cos t. And t we've just said is x plus 1, so cos of x plus 1. So therefore, the differential of this is just dy over dt times dt over dx. And so I'm just timesing these two together, and cos x plus 1 times 1 is just cos x plus 1. So overall, the differential of y with respect to x is minus 2 sine 2x plus cos x plus 1. And to be fair, in the exam, you could put this first just because it's positive, but it doesn't really matter. Yeah, this is year 2 differentiation. Okay, so that's how you differentiate that. Let's do another example. Okay, let's do another example. I'll just call that 1, 2. Let's differentiate x equals tan 3y. So remember, I want to find dy over dx. That's what the question's asking for. Again, like that last example, this is x in terms of y. So we're finding dx over dy. Now, what's the differential of tan? It's sec squared x. We've got 3 here, so it'd become 3 sec squared 3y. One thing I also want to mention as well, whenever you're working with any trigonometry in terms of calculus or differentiation or integration, you have to have your calculator in radians, not in degrees. Otherwise, when you start finding them at certain points, you'll get the wrong answer. So remember, always calculate in radians for differentiation and integration. Okay, so we found dx over dy, but we want dy over dx, so we need to do 1 divided by dx over dy to find it. So dy over dx equals 1 divided by this, which is just 1 over 3 sec squared 3y. Okay, so that's differentiating the trig functions. They can mix this up, and there is no sec on your calculator. It's 1 over sine. No, 1 over cos, sorry. There's not an actual button, but you will learn this in trigonometry and how to actually find values for it. So 1 over what was I saying? Sorry. Yeah, sec, so is 1 over cos. Okay, trying to think, should I do another example of that or move on? Okay, we'll do an example where we're mixing both exponentials and trigonometry together. That'll be an interesting one to test out all your rules. So find f prime of x of f of x equals e to the power of cos 3x. So we've got a trig function there, we've also got exponential. So this is chain rule because we've got a function and a function. So I'm going to let t equal this up here. And I'm going to let y equal e to the power of what I've just found, t. So dt over dx is just 3. The differential of cos is minus sine. So minus sine 3x. Now let's differentiate y with respect to t. The differential of the exponential is just the same thing, so e to the power t. And t we've just defined as cos 3x, so e to the power of cos 3x. Okay, so we've got now we just need to substitute into the chain rule. dy over dx equals, remember it's dy over dt times dt over dx. I wouldn't say memorize this chain rule, like rule, just understand that them two dt's cancel, which is why the chain rule works. So dy over dt, which you just said is e cos 3x times dt over dx, which is minus 3 sine 3x. Now, in terms of writing this out, I'll probably put my numbers first, then my exponentials, and then my trig. So it'd be minus 3 e to the power of cos 3x sine 3x. So I've just rewrote the order. So that's a good summary of just testing everything in terms of chain rule, exponentials, and trig as well. So that's a pretty good example. Okay, let's move over to product rule and quotient rule. And remember, with these, it might look complicated, but you get better the more you practice it. So product rule. What is the product rule? Now, the product rule you would use if you've got a function, so y, where you're timesing two functions together, so u and v. So as an example, I could say, which we'll come to, let's say the question said, differentiate y equals x cubed tan x. So you can see this is a function times a function. So to differentiate this, so i.e. it's y equals u times v, we use a product rule. And what does the product rule say? The product rule says that dy over dx equals, when you've got a function in terms of u and v, it equals u times the differential of v plus v times the differential of u. That's what the product rule says. Pretty sure they give that in your formula booklet, but the more you just tend to memorize it when you keep practicing it anyway. Okay, so let's use a product rule to do this question. I'm going to let u, so remember y equals u times v, where u in this case is x cubed, and v equals tan x, because I'm doing x cubed times tan x. So that's my u and that's my v. Now I need to differentiate each of these. Du over dx equals 3x squared, and dv over dx, the differential of tan x, remember, is sec squared x. We know that up here. We have to memorize that. So that is just sec squared x. So therefore, dy over dx, we just need to plug in these four into this here that we've just found. Okay. So u, which is x cubed, times dv over dx. So it's always like cross like that way, which you'll see. X cubed times dv over dx, which is sec squared x, plus v, which is tan x, times du over dx, which is 3x squared. So can you see how I've just done opposites? So simplifying that, dy over dx equals, we can just leave the first part as x cubed sec squared x, can't really do much with that. And with this one, I'm going to bring the 3x squared first, and it is 3x squared tan x. So that's how you use a product rule, and you use a product rule when you've got two functions timesing by each other. Okay, I'm going to do now an example of the quotient rule. Okay, so the product rules, when you time, does this always come up? I've seen this come up every year. And trust me, I think it's a really good question to have, because it's quite easy to spot when you need to use a product rule, but sometimes they mix the chain rule inside the product rule. Sometimes the product rule gets mixed into implicit differentiation. So you will use it somewhere, even if the question doesn't ask it that basic, it will be a lot more difficult. Let's go over the quotient rule. Now the quotient rule, so the product rule is when you've got two functions timesing by each other. The quotient rule, you use this when you have two functions that are dividing by each other. So as an example, I'm gonna just put an example here. Y equals, just find an example of this. y equals 2x squared minus 1 over 3x squared plus 1. So you can see with that example, we've got a function divided by another function, so you have to use a quotient rule for this example. Now, what does the quotient rule say? The quotient rule says if you've got two functions dividing by each other, then dy over dx equals v times du over dx minus u times dv over dx divided by v squared. So we're finding the same thing. We've got u, v, we're finding the differentials of both of them, but we're just plugging in different things into dy over dx. So let's do this example. Okay, I am letting u equal what's on top. So remember, your u has to be whatever's on top, v is whatever's on the bottom. So u is 2x squared minus 1, and v equals what's on the bottom, 3x squared plus 1. Differentiating each of these. So the differential of u with respect to x is just 4x, and the differential of v with respect to x is just 6x. Now it's just a matter of fact of plugging everything into the rule. So dy over dx equals v, which is 3x squared plus 1 times du over dx, which is 4x, minus u, which is 2x squared minus 1 times dv over dx, which is just 6x, all over v squared, which is 3x squared plus 1 all squared. Yeah, this is in the formula sheet, but it might be written a bit different in the formula sheet. So usually, I do remember from AQA it's written like this, but I'm not too sure about Edexcel if they do give it in this format. But you might see dy over dx equals v times u prime, because remember prime means differential, minus u times v prime, which means the differential of v, over v squared. So you just need to be careful of notation and check what it says on in your formula booklet. But it's the same thing, they do give you this, but again, with practice, you will just naturally memorize this formula anyway, but they do give you it, so don't worry too much about that. We need to simplify this. So I get dy over dx equals okay, 3x squared times 4x, 12x cubed. 1 times 4x is 4x, minus 2x squared times 6x is 12x cubed. And then I've got minus 1 times 6x, which is minus 6x, but I've got a minus there as well. Minus 6x is plus 6x. That's all over. I'm just going to leave that as is. 3x squared plus 1 all squared. They cancel out with each other. I've got 4x add 6x, which is 10x, all over 3x squared plus 1 all squared. So I'll just leave it like that. That's dy over dx. And again, they can say find the tangent of this or the normal, or find stationary points and so on. They can ask a lot of different things with this. It's just how you differentiate. Okay, so I'm just going to skip by the proofs. Okay, I'm going to do another quotient rule question just so you've got another example. Just in essence of time, I'm just thinking, is it worth doing? Have you guys covered parametric equations before? Is that something you've not seen before? You've not seen parametric equations. Okay, so parametric equations kind of involves I don't know how to describe it. Involves a chain rule, essentially, but I'll skip past parametric equations. What I will do is I want to introduce implicit differentiation because it's not too difficult of a concept. Now, implicit differentiation, so far, everything we've been doing is explicit differentiation. It's not implicit. So just to let you know as well, I've just skipped the parametric equations part just because you've not covered parametric equations, so you don't really know where they come from, but it's the same method of chain rule. So I'll cover implicit differentiation, and that's everything you need to know for differentiation. So implicit differentiation. Now, so far, you've been doing explicit differentiation. So you've just been differentiating. So let's say I've got y equals x squared plus 3x. I've got a function of y just in terms of x. So you've just differentiated y in terms of x. But what if I have something y on that side as well? This is where implicit differentiation comes into it, and that's where it starts getting a bit different. So just to define implicit differentiation. So it's used when you can't write an equation in terms of y equals f of x. So meaning your equation is going to be a mixture of letters. It's not just going to be x. So we call that an implicit relation. Now, let's do an example because it's quite easy to learn things with examples rather than giving rules, which don't make sense. So let's say the question said, find dy over dx of 2x squared y plus y cubed equals 6x squared plus 5. So we can see the clear issue here is we don't have y in terms of just something in x. So how do we find dy over dx? There's a few different rules with this. So I need to differentiate each of these terms. Now I'm going to tackle the easy ones first. Okay, so I'm going to differentiate with respect to x, and I'll show you what happens. So this one's the easiest one to differentiate in terms of x. So the differential of 6x squared, 6 times 2 is just 12. Decrease the power by 1, so we're just left with x. Okay. The differential of 5 is just 0. We know the differential of any number is just 0. Okay, so we've dealt with them two terms. Let's deal with this one next, because this one is a function times a function. So you should be thinking product rule. I'm going to be using product rule with that first term. Now the differential of y cubed with respect to x, you can't really do that because it's not x. So what we have to do is we're going to differentiate with respect to y. So we get 3y squared. But because we've differentiated with respect to y, we have to put dy over dx next to it. So that's just the rule that you do. If you're not, if you're differentiating a different letter, you differentiate with respect to that letter, so y, but then just stick a dy over dx after it. Now this one here, we have to use a product rule because we've got a function times a function. So let's do that over here. We'll do that separately. So remember the product rule says if you've got y equals u times v, then dy over dx equals u times dv over dx plus v times du over dx, or no, not all over v squared, sorry, that's quotient, just that. That's the product rule. So let's let u equal 2x squared, so the first part, and let's let v equal y. And let's differentiate each of these with respect to x. So du over dx, that's just in terms of x, so that's perfect. 2 times 2 is 4. And then x decreases by 1, so it's just x. Now let's differentiate this with respect to x. Well, we've got a y there. So just like up here, we're going to differentiate it with respect to y, but then add a dy over dx after it. So the differential of y is just 1. So we've got 1, but we need to times it by dy over dx. So I don't really need that 1. The answer is just dy over dx. So plugging everything into here now, dy over dx equals u, which is 2x squared, times dv over dx, which we've just worked out is dy over dx, plus v, which is y, times du over dx, which is 4x. Simplifying that, we get 2x squared dy over dx plus, I'll just say 4x y. Okay, so now I can say the differential of this, which we've just worked out, is this. So 2x squared dy over dx plus 4xy. Okay, so I have got all my terms, but I've not finished the question. I've not found dy over dx by itself. So that's the differential of each term and how you do that. Let me just write that out here. So I've got 2x squared dy over dx plus 4xy. I've got plus 3y squared dy over dx. That equals 12x plus 0, which I don't need to write that 0. Okay, so all I need to do is now I need to make dy over dx the subject of this formula. So dy over dx is over here and it's over here. I'm going to leave them two terms on the left-hand side, and this 4xy, I'm going to take it over to the other side. So I've got 2x squared dy over dx plus 3y squared dy over dx equals 12x and minus sig 4xy. Now to get dy over dx by itself, I need to factorize it out. Dy over dx times 2x squared plus 3y squared equals 12x minus 4xy. To get a dy over dx by itself, I need to get this over to the other side. Since I'm timesing by it, the opposite is dividing. So dy over dx equals 12x minus 4xy over 2x squared plus 3y squared. And that's my answer. So that's how you implicitly differentiate. So that's the last thing that they teach you in differentiation, and that's probably the most complicated one to it, but you can see how they're testing you in loads of different rules there. They've put product rule into there, they could sneak chain rule into there, they could put trigonometry into there. They're combining all your knowledge overall with that. And it can get more complicated. So I'm not going to go over the example for it, but I just want to show you, just because of time, and we've only got like 3 minutes left. This is a past question on an implicit differentiation question. So you can see here a curve has this equation. You can see a mixture of x's and y's, and it says find dy over dx for 4 marks. So you can see here you would just differentiate that as 3x squared. This one here, because it's y, you would differentiate with respect to y. So 3 times 2 is 6, and then y, but because it's y, you're doing dy over dx. Yeah, it's not a lot of marks at all. That differentiates to 0, and then this one here you'd have to use a product rule because it's x times y, and it's similar to what I've just done right now. So yeah, you would do all that for 4 marks. The next question here says point P lies on this curve. Find the equation of the normal. So remember normal, just like what we did before, y minus y1 equals m x minus x1 to the curve at P, giving the answer in this form. So can you see how this tells you which form to give it in? Where A, B, and C are integers to be found, which is whole numbers. So again, it's the basic differentiation which we did, but using a harder differentiation method, which is implicit differentiation. So I'm going to wrap it up there and stop the recording. I'll get this recording up. I'll send you the link to where the recording will be as well. So it'll be on YouTube, so you can skip through, have a look at examples as well. But that is everything you need to know for differentiation. The only thing that I did skip is parametric equations. That's because you've not covered parametric equations yet, but it just uses a chain rule. It's the same method as a chain rule. Yeah, if anyone's got any questions, you could drop them in the chat and I'll just stop the recording there.